Our next topic today in solid states is imperfections or defects in crystals. We have studied in this chapter the close packing in the crystals, and this perfect arrangement is possible only at 0 Kelvin temperature. As the temperature increases, there will be some defects in the crystals. And now how many type of defects are there in these crystals? These we divide into the three types. These defects are, first one is stoichiometric defect. Stoichiometric defects. Second is non-stoichiometric defect. And third type of defects are impurity defects. So we are taking first of all stoichiometric defects. What are stoichiometric defects? If a defect in the solids are such that ratio of cation and anion remain the same as represented by the molecular formula. For example, if we take NaCl, the ratio of cation and anion in this is 1:1 in this formula of NaCl. So even if defect will be there in that crystal, the ratio of cation and anion will remain the same as it is in this molecular formula. So we say stoichiometry of the compound will remain the same. Further, these defects are of two types. Stoichiometric defects further are of two types. First one is Schottky defect. Second is Frankel defect. Now, what is Schottky defect? From this defect, stoichiometric definition will be more clear to you. If, for example, we take a crystal of this type A plus B minus, like Na plus Cl minus, if we take, and in this crystal, equal number of cations and anions are missing. Equal number of cations and anions are missing from their lattice site. Then this defect is known as Schottky defect. And this defect is seen in the compounds with high coordination number, whose coordination number is high. And second is when the size of cation and anion is approximately the same. Example, KCl, NaCl, NaBr, alkali metal halides, mostly they come under this defect. And the fourth one I'm taking is the important point here. Density of crystal decreases. Because of this defect, the density of the crystal decreases. Now we are taking up how equal number of cations or anions are missing from their lattice site here. For this, I am taking a crystal. For example, this is cation, anion, this kind of arrangement we have. If perfect ordered arrangement is there. But now, due to this defect, what happens? From this crystal, equal number of cations, this cation and anion, equal number. If one cation I am removing, one anion also I should remove. Equal number of cations and anions are missing from this lattice site. And the places from there, they are missing. What will be created at these places? Holes will be created. So in Schottky defect, because of missing of cation and anion, holes will be seen in this structure. And density decreases because number of ions will be less now. If ions is less, then the mass will be less. So density will be less of this crystal. Next we are doing the Frankel defect. In Frankel defect, some of the ions are missing. In Frankel defect, some of the ions are missing from the lattice site. A point where ions are present are known as lattice sites. Some ions are missing from the lattice site and comes into the interstitial site. They are missing, but they are not leaving the crystal. They will come in the interstitial sites. That means density will remain the same because ions are not leaving the crystal. They remain in a crystal only. So no effect is there on density. That will remain the same. This defect is seen in the compounds with low coordination number. See the difference from the Schottky defect? Here high coordination compounds are showing and here low coordination compounds are showing. Size of cation and anion size differ a lot. The difference in the size of cation and anion. And examples are silver halides like AgCl, AgBr. These are the examples where we will see the Frankel defect. And for density, like I told you, density will remain the same in these crystals. Now in Frankel defect, if we are taking a perfect ordered crystal, cation and anions, but now in this defect, equal number of, one of the ions like this cation, mostly that ion is a cation, one of the ions are missing and that will come in this interstitial site. And mostly which ion is missing? Cation. The reason is cation size is small. And the small size cation can easily fit into these interstitial spaces which actually are very small in size. These particles that we have done, actually they are packed close to each other like this. This topic already we have covered up. And the size of the spaces, interstitial spaces are actually very small. And in these small size interstitial spaces, small size cations can easily fit. So that is why we say normally these ions which are missing are the cations and they come into interstitial site. And what is created at this site now? Hole is created. And remember, holes behave like positive charges. Holes behave like positive charges. So this is Schottky defect. And this one is Frankel defect. These are the two types of the stoichiometric defects. So see, if in this crystal we say there are 100 cations and 100 anions, cation and anion 100 are there, ratio is 100 is to 100. And if equal number of cations and anions are missing, suppose 2 cations are missing, then 2 anions will be missing. Now these will be 98 is to 98. So ratio first is 1 is to 1. Now also it is 1 is to 1 of cation and anion. So even if there is a defect, the ratio of cation and anion will remain the same. That means stoichiometry of the compound will remain the same. And here the ion is not leaving the crystal. It comes into interstitial site. So formula of the compound will remain the same. That is why these two type of defects are known as stoichiometric defects. There's one example that we have to learn, AgBr. This shows both the defects, Schottky as well as Frankel defect is shown by this compound. Moving on to the next defects, beta. Non-stoichiometric defects. Non-stoichiometric defects. Now, from the name, it's clear now. In a crystal, the ratio of cations to the anions is different from what is indicated by the molecular formula. So, as a result of a defect in the crystal, then the defects are called non-stoichiometric defects. And these are of the two types: metal excess defect, and next is the metal deficiency defect. In metal excess defect, this is further are of two types: metal excess defect due to anion vacancy, and second one is presence of extra cations and electrons in the interstitial sites. Presence of extra cations and electrons in the interstitial sites. So first we are doing anion vacancy, then we'll do presence of extra cation and electrons in interstitial sites in metal excess defect, then we'll do the metal deficiency defect. So moving on to anion vacancy defect. In anion vacancy defect, in this defect, a negative ion from crystal may be missing. And at that place, what will be created? A hole will be created, and this hole will be occupied by electrons. The hole created by the missing of anion is occupied by an electron. In this way, the crystal remains neutral. Remember, any kind of defect we have, the compound will remain electrically neutral. There will not be any charge on crystal. So if one anion is missing, one negative charge is less, but that will be completed by electron at its place. So charge will remain the same of positive and negative ions, and hence compound will remain neutral. Now to understand this, I am taking the example of NaCl. It's a very important question. When NaCl is heated in sodium vapors, it is heated in sodium vapors. What will happen? When sodium chloride is heated in Na vapors, then at the surface of this crystal of NaCl, Na plus ions will form and electrons will form. So see here, NaCl crystal I am taking here. And remember this, we have to heat NaCl crystal in sodium vapors. Positive negative ion arrangement, and it is heated in sodium vapors. So at the surface, these sodium vapors on heating will change to Na plus, and plus electrons are forming. So on the surface here now, there are Na plus ions present. So it will attract the negative ions. So some of the chloride ions from the crystal lattice are moving towards the surface to combine with these Na plus ions formed. So at this place, what will be created now? A hole will be created at this place. But now This hole is occupied by these electrons. From the surface, the electrons, they come here and they take up this place. This place occupied by these electrons here, known as F centers. F is taken from a German word Farb, and in Germany the Farb means color. So actually this NaCl sometimes turns yellow. Why? This is the question. Why NaCl sometimes turns yellow? So this whole defect we have to explain. Because of this defect, NaCl sometimes becomes yellow in color because of formation of what we'll write F centers in the structure. F centers are formed, so electrons are able to move here. When electrons are moving, this compound is showing a color. And which color? Yellow. In place of NaCl, if we are taking LiCl example, the color shown by this LiCl due to this F center defect is pink in color, and KCl shows which color? Violet color. So they show the color because of the presence of F centers in the structure. Now see, what is anion vacancy? Anions are leaving from here. So a vacancy will be created here, and that is in place of anion. So this is known as anion vacancy. And why this defect is under metal excess defect? So when anions will leave, as compared to that, the metals will be more in number. So this comes under metal excess defect. Now second type of metal excess defect is presence of extra cations and electrons in the interstitial sites. Presence of extra cations and electrons in the interstitial sites, that is voids. Now how will have extra cations and electrons in the interstitial sites? Example is zinc oxide. See, I'm taking the zinc oxide crystal here, and this also comes with heating. When zinc oxide crystal is heated, or it comes under the effect of heat, what will happen to this crystal? This is zinc ion, oxide ion. Since we are taking zinc oxide example here, this is white color salt. But due to this kind of defect, this shows little yellow color. So here you can get this question, why zinc oxide is sometimes yellow in color. So this defect will explain that on the surface of this zinc oxide, on heating, what happens? Zinc oxide changes to zinc ions, plus oxygen is formed which will evolve out, and electrons are there. So on the surface of this crystal, there are zinc ions formed and electrons formed here. So where these zinc ions and electrons, they will go? They will diffuse into the interstitial sites. They are coming into the interstitial site. So if zinc is coming here at this site, electrons will diffuse to the neighboring interstitial sites. Like here, the two electrons will come. See, if this zinc ion will come, the positive charge will increase. To balance the charge at the neighboring interstitial sites, there will be electrons diffusing. So because of this movement of electron, this compound shows a little yellow color. So again, this comes under the metal excess defect, because see, zinc ions here will be becoming more in number as compared to oxide ions. So this is a type of metal excess defect. So these are the two defects that we have covered up under the metal excess, and that metal excess is under the non-stoichiometric defect. So After that, in the non-stoichiometric defect, we have a metal deficiency defect. Metal deficiency defect. This type of defect is seen when the metal shows variable valency. This is shown by the metal showing when the metal shows variable valency. And the defect arises due to the missing of cation from its lattice site and presence of cation having higher charge in the adjacent lattice. Example, FeO. In this, Fe is with the +2 valency. So this shows +3 valency also. So this shows variable valency. We are taking this kind of metal which shows variable valency. So see the structure of FeO. The perfect ordered arrangement in FeO is like this. Positive and negative charges should be equal. So if this is +2, this is -2 oxide, ferrous, then oxide. This is called the perfect ordered arrangement. But now what can happen is ferrous here can change to ferric little bit, because when it comes in contact with air, some of the ferrous, they can get oxidized. So some Fe2 plus will start changing to the Fe3 plus. And if, for example, we are doing this, Fe plus 2 has started changing to the Fe3 plus, +2 charge we are removing and +3 we are introducing. But it will not be electrically neutral now, because one positive charge will be more. So what happens actually in these type of crystals? See, I'm removing the Fe plus 2. To understand this, suppose these 3 places Fe plus 2 I have taken out. That means how much charge I have taken out? +6. And at 2 positions we have Fe with +3 charge. That means if +6 we had taken out, +6 is introduced here. For every 3 Fe plus 2, at 2 places there will be Fe plus 3. That means at one place a hole will be created. Some Fe2 plus will change to the Fe3 plus. And for every 2 Fe3 plus, we'll say one hole will be created in this. And this kind of defect is metal deficiency defect, because this compound is of the Fe with +2 valency. So Fe plus 2 is less. Though Fe plus 3 has come, but the compound is of Fe plus 2. So metal here is deficient in this defect. This is the second type of defect, which is called the non-stoichiometric defect. After the non-stoichiometric defects, we are doing impurity defect. And this defect is also of 2 types. One is in the ionic solids, and second we'll do is in the covalent solids. Ionic solids. So first is in ionic solids, this defect. When molten NaCl, example I'm taking here is a molten NaCl. But when this compound is made, some impurity of strontium chloride is left here. So what will happen because of this impurity of strontium chloride? This is Na plus Cl minus. But in a compound, what I'm saying is there is impurity of strontium chloride. Compound is of Na, that is Na plus, while strontium here is your plus 2. High valency metal impurity when comes in this. So what will happen? This is just like this one only, but metal is of some other compound here with the high charge, high valency on it. So strontium will be here at some places where strontium will come with a +2 valency. At two places here, I'm taking out the Na plus to introduce the strontium. At two places, the Na plus are taken out, and at one place there is strontium with +2 valency. So charge will be equal. 2 plus charge is taken out, and at one place there is strontium. That means for every one strontium ion, one hole will be created in the structure. There will be one hole in this structure. So this kind of the defect is because of some impurity, but in impurity the metal is of the high valency, and this is found in ionic solids. Now moving on to the covalent solids. In covalent solids, the impurity is actually added. We dope an impurity. Impurities are doped in these covalent solids. Why these are doped? To change the insulators to the semiconductors. If we want to form semiconductors, then we are doping this type of impurity in the covalent solids. So now after doping an impurity, the covalent solids are changing to semiconductors. There will be two types of semiconductors, N-type and P-type semiconductors. N is from a word negative. So there will be actually electrons here. And P comes from a positive, and that is because of creation of holes in this covalent solid. And from insulators, because of presence of electrons and holes, they will become semiconductors. So let's see this part in detail. How in covalent solids, by doping an impurity, which kind of impurity we have to dope so that we can get N-type or P-type semiconductors. We are taking group 14 element. Group 14 element is like carbon, which has 4 electrons in its outermost shell. So it's a covalent solid, so all sides of this we will have the carbon only. And all these carbon atoms, they have 4 electrons in their last shell, which they are using to combine with the neighboring carbon atoms. So no free electrons are present in this structure, as all 4 electrons will be used up. So this element actually will be an insulator. Now, in this we are adding up, doping the impurity of lower group. Low group, like we can say group 13 element. This is group 14. To this we are adding the group 13 element like boron, aluminium, gallium, we can add to this, which have 3 electrons in the last shell. How many electrons they have in the last shell? There are 3 electrons here. So at certain places at the carbon, there will be the group 13 element. Let's say boron we are taking here. So here if I take boron, this has 3 electrons in its last shell, not the 4 electrons like we have shown here. Just 3 are left here. This electron is not there, just 3. So this is forming the bonds only with the 3 neighboring carbon atoms. At this place, no electron is here which can form a bond with this. That means what will be created here at this place? A hole will be created. So wherever the 13 group element will come, there holes will be created in this structure. Holes are like the positive charges, so they will also conduct electricity. So initially it was an insulator. Now because of the holes in the structure somewhere, some holes will be there, this will become conductor of an electricity. That is, this becomes a semiconductor now from insulator. But which kind of semiconductor is this? Like holes are created. Holes behave like the positive charges. So we'll say that P-type semiconductor is formed. So remember, P-type is formed by introducing an impurity of group 13 element. Now next one is N-type semiconductors, how they will form. So again, group 14 element we are taking, which have 4 electrons in their last shell to form the 4 bonds with the neighboring carbon atom. So no free electrons are here, so this is actually insulator. But now in this we are introducing a impurity, doping and impurity of higher group, like group 15 we are introducing nitrogen, phosphorus, arsenic we can take, which have 5 valence electrons. They have how many valence electrons? 5. So at certain places, when for example we say phosphorus will come, I am taking up the phosphorus here. For example, this is phosphorus. At certain places there will be phosphorus, but how many electrons they have in the last shell? 5 electrons. 4 will be used to form the bonds with the neighboring carbon atoms, and wherever there is phosphorus atom, there will be 1 electron available. So in the structure, wherever phosphorus will be there, there will be electrons present, and this will become N-type semiconductor now because of presence of free electrons. And electrons behave like negative charges. They are the negative charges. So that is why this is called which type of semiconductor? N-type semiconductor. So this is about the defects or the impurities, you can say, which are introduced in the crystals. Because of that, which kind of defects we can have? Imperfections or defects in the crystals.